This is the EnerFuel Materials Lab, and in here we do a lot of materials development work. Some of our membrane work was done in here, as well as some of the chemistry for the borohydride systems, the earlier borohydride chemical storage systems. And as of more recently, we've been doing seal development work using elastomers that are sprayed with a coating. This is a ultrasonic coating system, and we can spray elastomers onto bipolar plates or membranes or just about anything. Actually, it's CNC controlled, so we program the flow patterns, and then we deposit the Viton material and let that cure. Then we also have oven, press, some mixing stations for just any kind of miscellaneous materials work that we need done. Here we have some of the seals that were applied to the bipolar plates. And there's very fine, like a couple thousandths of an inch thickness Viton that had been applied. And we did since find that we didn't need that operation, so we've moved beyond that in the interest of cost. We also have some characterization equipment, some ultrasonic equipment for cleaning. Then we also have microscopes. We have optical microscopes for characterizing bipolar plates that have been exposed to acid over long periods of time. So some of our durability testing, we bring materials in here and we look for etching that's been going on or things that haven't survived the durability tests. Some more interesting materials work that we've been doing, which is the subject of some patents, is the use of highly advanced desiccant to remove moisture from the fuel cell systems. Since the phosphoric acid MEAs are subject to basically moisture from the atmosphere can leach the acid out of those membranes. Phosphoric acid is very hygroscopic. So this small cartridge is able to protect fuel cell systems and remove moisture and oxygen from those systems so that they can be used in backup power and that they can sit in the field for 10 years dry. And then when they get ready to start up, we know that the membrane's in the right condition. So this is some advanced work that we've been doing, patents pending on this one. And it promises to correct some of the issues that other high-temperature fuel cell companies face with basically moisture in the atmosphere attacking the membrane. So this system will prevent that from happening. Okay, this is the EnerFuel build room, and here's where we assemble the fuel cell stacks. This room has controlled temperature and controlled humidity, so when we open up the MEA packages, they're exposed to precise humidity and temperature. As you can see, we have some assembled stacks. These are 132 cell stacks. The shorter ones are like 32 cell stacks and some smaller ones for testing. These are basically previous generation fuel cell stacks, but they do include the external two-phase cooling. So the coolants are passed to either side of the fuel cell, and they're basically a single inlet per side. The coolant flows back and forth and then exits through this tube. And this is two-phase cooling, so we may pass DI water, which is vaporized, partially vaporized. And all of the heat from the stack is removed via solid-state materials to the outside where it is participates in the phase change of the coolant and is removed. It's a very elegant solution, and we do have patents pending on this assembly where the heat exchangers are actually used to compress the fuel cell stack. So there are no internal tie rods, and the coolants are completely physically separated from any of the electrical components within the fuel cell. And it basically gives us the ability to get a very uniform temperature and to use any coolant we want, whether it's very high pressure or whether it would be affected by the materials or the electric potential. By isolating the coolant, we have a lot of freedom in the coolant technology. We could be using organic coolants that vaporize at lower temperatures that could be used in organic Rankine cycle heat recovery systems. In our case, we use deionized water, which is captured from condensers. And that deionized water is then vaporized using the stack heat and sent to the reformer to provide hydrogen fuel. It's combined in the reformer with propane or natural gas, provides the hydrogen fuel, which gives us the reactants for the fuel cell. Here we do also do some leak testing. So we have a leak test fixture just to make sure that after we've assembled the stack, that the stack is leak free. This press is used to compress the cells, and then they're tightened. The hardware is tightened off. We have springs in there to maintain compression, so that as the temperatures fluctuate due to thermal cycling or the material, there could be some creep in the membrane materials. We account for that with the spring assembly. And we have a few other pieces of older hardware here, which basically have been used in, that was an automotive APU for a truck. So that was a 3 kilowatt ethanol fueled system, and we still have some of the stack technology in the room so that the membranes don't become saturated with moisture from the air. This is one of the 36 cell stacks which would be used in the Flexus 1 kilowatt fuel cell test systems. And what's unique about this stack is that you can see the multi-layer bipolar plate assemblies that run down the side. We have shiny layers and darker layers. And each bipolar plate is made up of multiple layers. The shiny layers have extremely high thermal conductivity in the plane, as well as electrical conductivity. The thermal conductivity of that material is higher than copper. However, the density is very low, so we're able to move a lot of heat, remove it from the cell to the external heat exchangers, which are mounted to the stack. And so basically, by using these multiple layers, the dark materials are used for molding the flow field features, and the shiny materials are used for removing the heat and, well, basically spreading the heat and electricity to give a very uniform potential field and very uniform temperature for each cell in the stack. The other thing that's unique, you can see the coolant lines penetrating through the top, and so do the electrical connections and also the reactant connections. Since the fluid doesn't come in contact electrically with anything in the cell, there's no chance of it picking up any ions or becoming contaminated by any of the materials in the stack. So these external heat exchanger plates are in thermal contact but electrical isolation. This is the EnerFuel shop, and here we have typical shop equipment. We have a lathe, CNC machine, some grinders, drill press, welding equipment. This is a sheet metal brake for bending sheet metal. As I mentioned, we have welding, grinding equipment, and some sawing equipment. So it basically has everything you need to do some of the final touch-up work on the systems. Some of the more complicated work can be sent out, but we can get a lot done with the equipment that we have, and it's all functional. And the people that have been working with it have been working pretty much in this facility with a lot of this equipment for 20 years now, so we've got a lot of productivity out of it.